I'm Andrew Glick. I have a fair bit of OpenSCAD experience, and I think it's a cool thing that I'm excited to show off to you all. So, what is OpenSCAD? In short, it's CAD with code. So, your traditional CAD workflow that you may be familiar with from programs like SolidWorks or Creo is something like you have a sketch, then you extrude that sketch, maybe make a hole, and then you put the hole in the sketch, and then you have the whole thing together, and that's the general workflow. In SCAD, it's a little bit different. There is no sketches, there are no extrusions really. It's all done with code. So here we can start off with a square, this same size 10, specifying that it's centered. Then we could also extrude the square, get a cube, and then we can cut a hole out of it with the difference operator. And well, I'll talk about all that stuff in a bit. But we translate we create a cylinder, rotate it, translate it up, and perform a Boolean operation. And don't worry about the FN on the top line, that will be explained later. So why use OpenSCAD? Well, for one, it's free and open source software under GPL version 2 license, which is a lot more than you can say for most CAD programs like SolidWorks or Creo. Even though you may be able to get those for free with a student license, ultimately they're not free. But OpenSCAD is free, and it will always be free and open source. So you can guarantee that anyone else will have access to it. It's powerful. I think that's kind of a oversaid thing for these workshops. Like, oh, look, we're introducing this new technology. It's really powerful. I don't think we would be showcasing something that wasn't cool, but I think it's worth saying nonetheless. Another big thing is it's very strong with parametric designs. So because everything is with code, you have complete control over everything, and it's very easy to parameterize your designs and make them very customizable, which segues into the customizer, which is a built-in function of OpenSCAD, and that started from Thingiverse, which is a 3D printing design hosting site. They created a customizer for you to easily interface with OpenSCAD parts, and then OpenSCAD has since integrated that into their own platform. Also bragging rights, because it's pretty cool to say like, yeah, I CAD'd this, but it's even cooler to say I CAD'd this with code. So if you want to take a look at some examples, this is one of the most common ones from OpenSCAD is the gear bearing by Emmett. This is a print in place planetary gear set with herringbone gears. So the teeth are actually angled. They're all chevron shaped and fully designed in OpenSCAD. It's really, really cool. Also by the Thingiverse user Emmett, the screwless gear cube, another classic, also designed in OpenSCAD, it's a cube that is also gears, as you can see. So also really fascinating design. And a bit more abstract, or a bit larger, more professional project is the Prusa i3 3D printer. Although this isn't the current iteration of their 3D printer, there's all of their designs, even up to the current versions, all their files are available in OpenSCAD because you can guarantee that someone else is going to be able to open those files and work with them. Here's it's a design by me. Look at that. This is a flower based on the Fibonacci sequence that I designed. And although this isn't necessarily easily 3D printable, as I can say, because I've attempted to 3D print it, even from an artistic standpoint, it's OpenSCAD is a very powerful tool. So all of the each layer of the flower is based on the Fibonacci sequence. So there's if you're not familiar with it, it's the 0, 1, 1, 2, 3, 5, 8, and so I think that's right, and so on. The sequence, and each row of petals or leaves is based on that. Here's a strand beast that someone made in OpenSCAD, and it is animated, and just so cool to watch these things for one, and for second is, it's just a strand beast. I don't think I need to say any more. So then other features. So as I mentioned, we got the customizer. So you're able to change all the various parameters of the model. And yeah, it's very, very cool that you're able to do that right from there. You don't have to touch any of the code. There are also libraries. So this is a library called MCAD, which is packaged with OpenSCAD. And that contains things like gears, bolts, more gears, and yeah, you don't really have to do a whole lot of work here because all of the these are all parameterized, I guess is how you would say that. Um, Libraries where you're able to um, use the things that other people have made and very easy to integrate into your projects. So now we'll get into coding. Can you still see the blank screen that I have up here on Teams? Thumbs up from anyone. Unmute. Maybe. Um, I'm just going to go ahead and hope that all is going well on the recording. So I'm going to be using the OpenSCAD extension for Visual Studio Code that I also wrote because I like it. The OpenSCAD itself has an editor built in. Actually, you can see right here. Here is the gear bearing. So well, just for the sake of example, if we increase this, you can see that it automatically regenerates, and the visual or the graphics kind of get a little glitchy in the preview mode, but if you spend some time to actually have it render out, then it's fine. We can also change parameters like that, and it makes it taller, and so on. But like I said, there's the built-in editor. I'm gonna hide the customizer. But I am not the biggest fan of this personally, just because it's relatively simple in terms of code editors. So I like having a code editor like Visual Studio Code, which is my go-to editor, and I wrote an extension for it so that OpenSCAD will work in it. So I'm going to be using that, but feel free to follow along in just standard OpenSCAD. It's exactly the same. So first things first, let's make a cube. So in the PowerPoint that I showed, I used a square and a linear extrude. That's actually not super necessary. We can just start off and type cube. So we put parentheses, and then we can just say size equals 10, and put the semicolon, and then I'll save this, and I will open the preview here, and I'll there we go. There, okay. So we have a cube. Confirmation that you all can see, please. Anything? All right. Just gonna keep on going. So in addition to just having a cube, because that's great and all, we can also specify the size. And I should also note for any of you may be listening, that feel free to interrupt me if I'm going too fast, as I likely will go pretty quickly. If this is recorded, you can always pause the video, as you know. And also this workshop, or the tutorials are heavily based on the official OpenSCAD tutorial on their wiki. We will be linking to all of this code either on GitHub or OneDrive or somewhere, so you have access to it as well after the workshop. Yeah, just wanted to mention that too. Anyway, so we have our cube of size 10. If we want to have a box of different dimensions, list here with the angle brackets, and then we're specifying X, Y, and Z size. And if I save that, we can now see we have a box. If we want to center that on the origin, we can just say center equals true, and it's centered. So let's try and make a shape. So if we adjust these values, we get a different shape. And let's try adding another cube now. So if we add a cube and say this is 30 in the x direction, 20 in the y direction, 10 in the z direction, and if I don't put the semicolon, it'll give us a syntax error down there. But I do that, and okay, we get another box. I forgot to say center equals true. If we do that, then we can see, oh, we don't even see the other box, and that's because it's and I mean we saw that it was there a moment ago because I forgot to put the center equals true, but the boxes are completely overlapping, and you can't see the second one because it's smaller than the first. So what we can do is let's move up that second box so it's above the first one a little bit. So if we translate the second one, we can do 0, 0. So this is in the x, y, and z direction. So let's do 5 just to start out with, and we can specify it like that, or let's just leave it like that. So now we have the two boxes. We can increase this number even further. This gets to 10. But if you notice that the boxes are 10 tall, or 10 units in the z direction already, and it can be kind of confusing to OpenSCAD when you have two faces intersecting each other right there in the middle, because they're both at the same height. So because of that, it's generally a better idea to say maybe translate minus 0.001. You can't really tell the difference, but OpenSCAD now is able to tell that the two boxes are overlapping versus just occupying the exact same space and not really being sure how to handle that. Of course, you could write 9.999 or something, but I think 10 minus 0.001, it's a little bit easier to read just because it's more clear what's going on. That it's translating up 10 units, but we're taking back just a little bit rather than translating up 9.999 units. I just think it makes a little bit more sense to do it this way, and I'd rather spend a little bit more space typing if it saves some cognitive load later on reading this. As you'll see, because the code can get kind of long, especially if we have everything on one line like this. So it can be nice just to put each new statement or each function or operator, however you want to call it, on its own line, like this, and just indent it so it's easier to see. But it doesn't really change the effect of the code. It's still working exactly. So we have a very basic shape that might make you think of a car. So let's make it a car, shall we? What we can also do is we can translate this this box back a little bit. or actually forward because this is the positive direction, but the car is facing in the negative direction, which is not a problem. And let's add a wheel now. So we can add comments. So this is the car body, and this is a wheel. So a wheel would be a cylinder. So we can say h equals 3, and actually, well, it doesn't matter the order, but I'll say r equals 8 for the radius and h equals 3 for the height. And we save that, and we can see, oh, look at that. Can't see it because it's in the middle of the existing model. So if we comment this out for a moment, we can see that we do indeed have a cylinder here. So yeah, let's add a transformation like we did with this cube here. We can translate this down by 20. So 0. Actually, oh no, we translate it to the side because it's a wheel. We don't need to translate it down. And if we do that, then we can see that the wheel is there. And let's add a rotation to it as well. So let's say rotate, and we want it to go on the x-axis, so that'll be 90, 0, and 0. And oh, okay, so the wheel is now at the bottom. And this brings up to an important point, is that the order of operations or the transformations that you apply to the mesh or the objects, they matter. So if we translate and then rotate, we're rotating about the origin on the x-axis, so it's going to move the wheel down there. If we want the wheel to be rotated and then translated, we just have to flip the order of that. So if we do that, we can see that we rotate it first and then translate it. And I guess you kind of have to realize that it goes backwards, or that it's applying the translate to the rotated cylinder and it's applying the rotate to the cylinder. So then we can move this into position. So let's move this to -20 and -15, and that moves the wheel up to the front of the car. And if this process looks like it's going really smoothly because I know exactly what numbers to put in, that's because I know exactly what numbers to put in. This is very often just a tweaking exercise of like, okay, we want it to go up maybe 20, or we want it to go out 20. It's like, well, no, that's a little too far. So maybe we try 17, or we try 12. That's too close. If we try 10, that's like directly in the car or on the side, the edge of the car. So we'll do 15. So it's not the a straightforward process always, but just don't let that discourage you. So what I can do is I can copy this line down a few more times, and I'm just going to flip around the negative signs and so on. So we have -15, 20, -15, -20, 15, and then 20 and 15. There we go. We got all 4 wheels. And one other thing you may have noticed here is that these are not circles or cylinders, right? Like if you're using Creo or SolidWorks, you would get a perfectly smooth circular face. But that's not the case in OpenSCAD, and that's because this is a meshing program. So you're working directly with a mesh, and there are no circles in a mesh, just flat faces. So by default, it'll approximate a circle, and you can change that number, as we'll see in a bit. That's just something to be aware of. And yeah, so we got the wheels. Let's add the axles now. So we'll do a complete axle that goes all the way through the car. And as you probably noticed, this car is looking a little lopsided, and that's because I forgot to center the wheels. So if we do cylinder and we say center equals true, there we go. We got that one lined up, and I'm into the other ones. There we go. Okay. So let's add the axles now. I'm working from notes. we'll start from the base. So we'll do a cylinder. We'll say that this height, or the height of the cylinder, is going to be 30, because our wheels are plus or minus 15. So 30 will get to both of them. Then here we can say the diameter is 4. And like before we specify the radius, we can also specify the diameter. And we'll also say that the center is true. And if we save this, oh, I forgot a semicolon. Yep, there we go. We get an axle right there, and let's rotate that into place. So rotate 90, 0, 0, and we need to translate that up. So translate minus 20 and 0, and I'll indent those. And then let's also copy this and do plus 20 for the rear axle. All right. So now let's talk about the circles, because as you can see, it's much clearer with the axles, where they're very much not a circle. The wheels here, they're close enough, or they're large enough, or they have enough faces that you could that's a circle. But the axles here, those look more like a hexagon or an octagon or something. So what we can do is we can OpenSCAD has these special variables. There's FS, FA, and FN, which refer to the size of the maximum size of the segments, the size of the angles between the different faces, and FN, which is just the number of faces. So what we can do is we can just say FN equals 50, and then it's going to use 50 faces for each of these. Or if we want, we could also say FN equals 100 and get a much finer resolution. But of course, this comes with the trade-off that with higher resolution, especially with much larger models, that it can get it can really start to slow down your performance. So you can always reduce this and then turn it back up later. So this is just a basic car, but I think a very important part of every car is having a needless little statue on the front for aerodynamic reasons, or I guess I should say for coolness reasons. So let's put like a little emblem on the front, like maybe a triangle or something, or just a upside down triangle, just because that'll probably look cool. So let's we're gonna want to translate it. We'll do this forward by 30, because that's half of the car, and let's just have it go up by 10. Just to get a rough idea, we'll rotate it. In the past, we've rotated about the x-axis here on this plane to get the wheels, but we want to probably rotate it along the y-axis here on the green one to get it, as car emblems go, or whatever they're called. So let's rotate on the y-axis here by 90 degrees, and then let's add a cylinder of radius maybe 3, height of 1, just for the thickness. And then here, because this is just gonna be a circle, we want a triangle. There's not really a triangle tool in OpenSCAD, just circles. But what we can do is we can manipulate that FN variable and say we want 3 faces, and there we go. So we got a little triangle, and that's cool, but it's kind of floating above the car, which is not great if we want it to be attached. So we can move this down some, and maybe we can move it back to a little bit. So let's try 29. Okay, well that's a little bit probably too far in. So we can pull it back up maybe to like 7. All right. So there's our CAD, or not our CAD, our car designed in CAD. Yeah. So now let's add parameters, because this seemed like quite a bit of work to get just this car, but this is not, we're not fully utilizing all of the power of OpenSCAD here. So I'm just going to make a new file. Actually, no, I can just work from this one. All the files are here. So let's add some parameters here. So what we can do is we can say, let's have one for maybe the wheel radius. We said that the wheel radius is 8. And then we can just go and substitute that. So like wheel radius, I can spell, which I can't, but thankfully, this is why I like having VS Code here, is because it makes some of this stuff a little bit easier. So if we change this, no change, but that's because we just use the same variable. If I increase that to 10, all the wheels update. If I change this to 50, we get, big car with like CDs for wheels, thinking if it's a toy car. Let's see, what else? Well, we probably also want wheel spacing. And what we said that that's 30 between the two, because it's plus 15 and minus 15. So then this would be wheel spacing divided by 2, and I'll just copy that and there, put that there, put that there, and then here is just wheel spacing. Once again, no change, but now if we wanted to increase the spacing, bam, car's bigger. Or we could go. We could also do the axle spacing. So that'd be this distance here, and let's say that that's 40, right? Because we're going 20 forward, 20 backwards. So axle spacing divided by 2, because we have 20, and fixed all those. And if we want to increase this now, we can keep on going. Now the car really does not have wheels attached to it at all. Let's bring this back to be 40. We can also specify the width of the car. So if we wanted to say the width is 20, and we'll also do the length while we're at it is 60. So we'll change this to width, or no, that is the length. We got the width, also the width. Nope, that's the length. There, I think. Oh, and then we also want to do length divided by 2, and also plus 1, because we're so it's negative length divided by 2, so then we're plus 1, so because it flips the negative. And I meant to do length divided by 2. There we go. And now we have complete control over all of these various parameters. Not quite everything. Like we don't have the emblem. Maybe we could add something for, or we could add the diameter of the axles. But for the most part, we have the everything parameterized, I guess. What else we could do is we could say, well, maybe we want the axle spacing to be proportional to the length. Because we probably don't want to have a really short car, and then the axles are no longer inside of the car. So let's say maybe that if we're looking at this ratio right now, we have a 3:2, so we could just say that this would be equal to length divided by 3 times 2 times 2/3. I guess 2/3. So now axle spacing is not a variable that we have to worry about. It's just controlled through length. So if we change this to 80, it also updates. Or maybe we realize that we probably don't want it like that. We want it, if you want it like maybe the length to minus 20 or something like that, you could also do that very easily. Very easy to customize here. All right. So now let's get into some of those Boolean operations that I had mentioned. So let's add a name to the top of the car, just because, and because I'm adding my name, or I'm adding a name, I'll add my name. So the way we can do that is we can actually do that with the text. And what we can do is we can specify text. I'll add Andrew. If I just render this, we can see we got Andrew.
Yeah, I can't hear you anymore.
Okay, can someone say something?
I can, yeah.
Okay, yeah, okay.
I can hear you.
All right. My headset died. That was weird. I thought it was charged. Anyway, you're able to see the screen, right? Just wanted to make sure that I'm not talking to empty. Okay, yeah, great. And feel free to interrupt at any point if you have questions or having trouble following along or anything. Yeah, so we can see we have my name there. Actually, there's a special symbols in OpenSCAD that we can use for rendering only one thing at a time. So I think that's the exclamation point is just going to render that single thing that you have applied it to. And actually, another thing that I had forgotten to mention is yet another reason to use my extension is that OpenSCAD by default comes with this what's called the OpenSCAD cheat sheet, which just is a easy reference of all of the where's the cheat sheet? Just a very easy reference of the various functions of OpenSCAD, including the these four modifier characters that I can never seem to remember. However, I have that built in. So all of the entire cheat sheet contents here are built into the extension, and you can just see the reference to them at any point in time. So very useful thing, especially because some of these can be really hard to remember. But anyway, here you have the show only. Yeah, let's get back to yes. Okay. So that's a little bit big for the car. We can say the size is smaller, so like size equals 5, and then we can also align it with the origin. First I will translate that up. So we'll do translate 5, 0, and about maybe 15. There. That translated up, and actually we don't need the exclamation point anymore because we have the car. So what this is doing is this is placing the text based on the origin here, and we could probably move with the translate. I should not have added that 5 because that's confusing. Yeah, so we could probably move that into place by messing around with it, but it probably wouldn't be exact, and depending on the length of your name and just the width of the characters, it could change to get that centered on this piece here. So what we can do is we can just say h align equals center, and also v align. And what that does is that will center it, and then here's where I added the 5, and that will put it centered on that block. And so yeah, there's a like if you wanted to be raised, you could leave it like that, but I think it would be cooler if we could cut into the top. The way we can do that is with the difference function. So if we say difference, and then we'll use brackets. And you can use brackets on any of these, on the translate, on the rotate, and so on, if there's ever multiple things. So in this case, we're taking the difference. So it takes the first one, and then everything else it subtracts out of that. So if I run that, did I? Oh, I think is that's too high. So if I lower this down some, so maybe like 13, will that work? Oh, I also forgot to extrude the text because it is a two-dimensional shape. So we need to extrude. And if the top is 15 up, because we've gone from the origin, we went up 10 to where this box is, and then it's 10 tall, so that's 5. So we can do 10 plus, let's do 0.01, so we can, yeah, just so we go a little bit past. And there we can see the, yeah, there's my name. And if it, if you probably want to add a variable for the text thickness or the depth of the text. But I'm not doing that right now. But if you wanted to, you'd probably want to have it something like 15, where that was the height of the car, and then the text depth, which is 2 here. One thing here that I did is that I added the text directly to this cube. But if I wanted to add the text to the entire car, for instance, I couldn't do that with this technique, because if I say did a difference here, oops, and then if I move this bracket down all the way here, well, that's a little awkward. We got like a little cutout there where that little triangle is, and we have holes through the sides of the car. We don't really want to do that. That's not exactly what we want. And like I'd mentioned, that the difference takes the first thing, or the first child here, in this case the cube, and subtracts everything else out of that. But we don't want to do that. First, we want to create a union, which is to combine all of the parts together. And this, and indent that over. So there's a combination of the car body, and then we can take a difference from this union. Do that. I did not want that. How do I unindent? Okay. We'll just unfold all of these regions. There we go. And then we can add our text down here, and that would work. And I just wanted to show that this is how you would do it, but I think the first one where we were just cutting out of this first cube is probably the cleaner solution. So I'll just leave it there. But like I said, I just wanted to show that that's how you would do that. All right. So let's make the wheels a little bit more advanced now too. Rosmo, it's at 7:50. How am I on time? Do I need to stop at 8, or can I? Because we start a little late.
I mean, you're good on time as
Okay.
far. I mean, as whenever you finish.
All right. Okay then. Then we can make some more complex wheels. So I'm just gonna make a new file here called wheel, so we can work with that without having to look at, or without having to deal with the car, because I just want to work with this in isolation. So we can use different shapes for the wheels. So what we've been using is we've been doing cylinders, but we could also say, maybe if we wanted a sphere, we could say that this is maybe with a radius of 8. If I save this, and of course it's not going to preview because we are not previewing that. So I'll open up a new preview here. So yeah, we could use the sphere, although probably it'll be a little weird to have spherical wheels. So what we could do is, like, maybe let's cut out some spheres on either side of it, and then we'll be left with like a slice down the middle. So the way we would do that, as I just mentioned with a difference, is we can do a difference of the sphere, and then also we'll need to translate over, you know, let's, actually, I will make some variables for this. So we'll have the radius of the hubs, the hub radius. We'll say that that's 10, sure. We have the side radius. Let's call that 50, which will make a little more sense in a bit. And then we'll also say the wheel thickness. So hub thickness. We'll call that 5. So hub radius is, we should be using variables here. So the radius of the sphere is the hub radius. Then we will translate over 0, then the side radius plus the thickness divided by 2 and 0. So that's just going to translate over on the y-axis. And then let's make another sphere with our equals. If I save that, then we can see, okay, we have a larger sphere, and then we've also cut out a chunk from here, but it's not exactly a spherical shaped chunk, as you can see, because if you have a super big sphere, I think if we use this percent modifier, that'll allow us to see it in debug mode. So yeah, it's a really big sphere, but it's not a high resolution. So we can use these the special variables that I mentioned, fs and fa. So we can say fs equals maybe like 0.4, and then fa equals 0. Or fa equals 1. If I re-render this, you can see that it's a much finer resolution, but it's also quite a bit slower. And that is probably going to be dependent on your computer. Screen sharing. But if we decrease this down to a little bit more of a reasonable size, we can like FA is 2 and FS is 1, then we can get a little bit more reasonable, get some better performance. So if I duplicate this here, and instead we translate negative of this distance, we can cut out the other side of the wheel. Yeah, so that's great and all, but it's the way we did this car here is where we copied and pasted the wheel each time. I feel like that would get really tiring with this more complicated code, especially if you have to change anything. It's like, we have these parameters, which is great, but if we wanted to change maybe how the parameters are used, or if we wanted to add in maybe holes or something for like the spokes, it could get very difficult. So what we can do is we can actually create a module, which is the same thing as a function you probably have in other languages. A function in OpenSCAD is more of you could think of as a mathematical function, where you have an X or a Y input and you get an output. But modules are more of the doing thing. So what we can do is we can say a module called wheel, and I'll just move that there. And if we render it, oh no, we have nothing. And that's because we did not actually call our module. So if we say wheel, then we can get, then our wheel renders. If we want to translate our wheel, we can do that. So translate 0, and we'll go up 10. There we go. And the other thing we can do is, so maybe we want to be able to specify the parameters to our wheel. So if we wanted to be able to say that, or when we create a wheel, if we want to be able to say, like we want the radius and the width of it, we can do that. So maybe we want a hub radius and a hub thickness, and we could also add side radius, but I feel like side radius is probably dependent, or would be dependent on the hub radius. like that seems like a side radius is really just hub radius times 5. So we could just say side radius equals hub radius 5. Oop, forgot to include that there. Oh, it doesn't like that I didn't pass any parameters to it either. But now we can have these local variables here as you would be writing with a function. We have hub radius and hub thickness, and then we can pass hub radius and hub thickness. And if we do that, then we have our wheel again. And we can also take these special variables, and if we don't want them to conflict with anything else, we can put them in there. So, and another thing is like as these are, different variables, we could also call like this is hub radius, another name, and then hub radius, another name, and it's fine because this is this variable, and then this hub radius is for inside. So I'm gonna copy this back into our car. Now we can use this wheel. So if we want to change this, where we have the cylinder, we can just say wheel, and then we have wheel radius and we have wheel spacing. So we probably also want to add a wheel thickness. That's what we call the hub thickness in the previous one. So we'll say wheel radius and wheel thickness, and I forgot the semicolon. And if we go back here, so yeah, so that's rotated now because we had the rotate before for the cylinder, but we don't need that now because the new way of our wheel is constructed. So yeah, there's our new wheel, and then we can just copy this down, and we don't need these lines either. And there we go. So there's the car with the new fancier wheels. What we can do is we can actually just say, let's just make this whole car its own module, right? Because maybe I want to have I want to be able to call the car. Actually, while I'm thinking about that, I'm going to make this text variable. We'll make that a variable called name, and then name equals Andrew. It's not going to change anything, but now that's just up there. So let's make so this is a wheel. We create a module called car, and if you wanted to pass the axle spacing, the wheel radius, the length, the width, and so on, you could do that. And if you're probably going to make this a real thing, you probably would want to. But for the sake of this tutorial, I am not going to. But if we copy all that stuff into the module, once again, we get nothing, and that's because we're not actually calling the car function. But if we call car, then we get our car. And it's cool because we can just translate the entire car. Translate. Let's translate this 60 forward. Yeah, so 60 in the positive direction, which is backwards for the car, of course, because that makes total sense. But we can actually do some cool things with this now, with loops. So if we have our car, we can actually write a for loop because OpenSCAD has those. And let's go. We'll just say y because we'll start in the y direction here. So we can go from 0 up to let's say 5, and then we'll add some brackets here, and we can translate then translate, and here's where the y comes in. We'll do y times, let's just do 50. we'll increment each for each y, and then we'll do 0 again. If we do that, then now we get 5 cars. And this is starting to hinder my performance a little bit because we got a lot of those giant spheres being created. So what I'm going to do is I'm just going to comment this out, and then we can just say and this is the same code that we had before, where rotate 90, 0, 0, and then cylinder r equals hub. Yes, hub radius, and h equals hub thickness, and then center equals true. There we go. We changed all of the cars at once, and with the old simple wheels, but it's way smoother now. So yeah, so we did a very basic for loop here, and what we can do is we can actually specify, maybe if we wanted to say we wanted like num cars. Oh, teams. Oh yeah. Thanks for coming by. Yep. And then we so if we say maybe we want 6 cars, and then if we want the spacing, so like y spacing equals 50, then we can change this. So instead of going from 0 to 5, which we could do, we could go to 0 to n cars, and then we could just do this as like y times y spacing, or I think that might change it a little. Oh, I forgot to spacing. There we go. Or we could also say that this is going to increment by y spacing amount, and it's going to go up to n cars times y spacing minus 1. And that's going to be huge if we do that. There we go. So yeah, we could do it that way. So I'll leave it like that, and then we could also let's do a in the x direction as well. You know, for x from 0, and we probably need let's just say n rows. Rows of cars. We get that. Let's say that's 5 maybe, and then x spacing equals 70. I prepared this, so I know that those values are good. Let's go by x spacing. Up to n rows times x spacing minus 1. Also get our brackets here, and we can translate that by x and y, and do that. Then we have a entire fleet of cars, and they could you know, it's a fleet of cars. What more can you ask for besides an even bigger fleet of cars? There we go. And yes, okay. So I'll bring this back down to 6, and I'm going to comment this out. And there's another thing we can do with for loops, and this is maybe my more favorite application of for loops, because it's cool and all to translate cars and all that, but I think it's cooler if you can rotate them too. So let's do for theta equals 0 up to n cars, and this we will create a car, and if we rotate the car by theta, just if we do 360 divided times 360 divided by n cars, what this will do is just say we want this to go up, or we could say this, we want this to go up to 360, and it should be incrementing by 360 by n cars. N cars. Right. So maybe that makes more sense. So we could do it. We did the other way for that one, so we'll do it this way for this one. So we're going up 0 to n cars, and then just take my word for it that this is going to rotate each car or each theta by increments so that it's evenly distributed. So if we run this, this is kind of a mess. The W's came out though, so that's cool. And maybe maybe this is like a weird circular bench in a park with W's on it, and then like weird things that make it really awkward to sit on them. So, but this isn't really all that useful. And full disclosure here, but this is where we can exploit that translate, or the fact that translate and rotate happen in a different order. So if we maybe say like a car radius as opposed to like the wheel radius, so maybe we want the cars to be in a circle of 200, and then we can say car radius 0, 0. If we do this, then we have a ring of cars. Actually, we could probably decrease this a little bit just so we can see a little bit better. And so maybe now, so now we have a ring of cars all facing the origin, staring down. Who the origin itself of something. I don't know. There's a joke there probably. But maybe we want the cars to be going in a circle. So what we could do is we could apply another rotate before the translate. And actually, and I did it here. But if you don't specify a set of coordinates here, so like x, y, z, you have to do it for translate. But if you don't specify for rotate, you can just have it rotate about the z-axis. So here, let's just have it rotate 90 degrees. And then now we have cars going in a circle. We have more cars. Yeah. So there, we got a bunch of cars. So that's basically it for the car example. That was actually like exactly an hour. So look at that. But I have another example of making something just something cool, because car like little model cars are great and all, but yeah, here's another thing. So we'll call this pencil. This one of the most important parts of 3D printing is 3D printing random knickknacks and gadgets and stuff, or this isn't a gadget, but just random stuff for your desk. So in this case, we want a pencil holder, because engineers, we have pencils or pens, or a bunch of styluses because we're all digital. Who knows? So I'm just going to wrap this up relatively quickly. I already have this written, as you can see, it's down there. But I'm just going to go ahead and variable. So this is also in degrees, which will kind of play a little bit. Diameter is 50. Height equals 100. Wall thickness equals 1.5. That actually I don't even reference it in this one. No, wait, I do. So let's get this preview going. Okay. So first thing, we shall create a square of size 4, and it'll be centered. Yes. Okay. Now I'm going to rotate that square by 45 degrees so it's offset just a little bit, like so. And we will translate that square by the diameter by 2, also known as the radius. Translates it out there. And then we're going to do a linear extrude. You're like, oh, okay, so this is, we're going to have like columns and stuff. Well, almost. Linear extrude has a cool feature. So if we, well, let's just one thing at a time. We can do height equals height, and then we'll just leave it like that. So if we do that, then we get a column, and we could do a for loop. So we can say I equals 1 to sides, and put that in there. Oh, and I forgot to rotate here. So then this would be I times 360. Yeah, so we got like a circle of pillars. But linear extrude actually has a really cool thing. I'm going to, for the time, disable the for loop, which is that you can apply twist to it. If we just if we apply, so we just have that. So if we apply a twist, we can say twist equals, in this case, then it twists it as it extrudes. If we go even further, we could say like 360. We create a twist, and it's pretty cool looking, actually. And we can also specify the number of slices. Oh, that increases it in this case, to make it a bit finer. But what we can do, I'm going to put this back. Twist is if we rotate, which we did before, it doesn't do much. But if we translate it, now it's going to be twisting the linear extrude is about the origin. So when we apply this for loop, we get this really cool helix, which is I think my headset died again. I'm not really sure what's going on. So hopefully you can still hear me. So yeah, so this is the helices. Then we can also create a base for this. So we have a base. Actually, I'm just going to indent that just because. So let's make this a cylinder of d equals diameter and plus 10, just because it's going to fit a little bit better. Height equals base thickness, and I'm actually going to change that to 2. And Fn equals sides. And I forgot a semicolon. Okay. So now we've added a base to it, and that's cool. I think, just personally, I think it'd be cooler if the flat sides of the base were in line with the helices bases. So I'm just going to add a rotate of 360 divided by sides, and also divided by 2. Or I mean, this would be the same as sides times 2. So yeah, there, that has rotated that now, and yeah, looks pretty cool from the top too. And then let's add a top to this, because these will break right off. We can do a translate. We'll need to translate whatever we're doing up height amount, because the pillars were extruded up by height. And I'm gonna skip that. We'll work from the bottom up. So let's do a circle of d equals 4. And let's I'm going to comment this stuff out for now. So there we have our circle. We can translate this out by the diameter, by the radius, I guess, in this case. So translate that out. And now what we can do is we can add a rotate extrude. That does is we have a ring. So that it's rotated, it's revolved this around the origin, around the z-axis. And because even though the circle, when it's shown here, that it looks like a 3-dimensional object, that's just OpenSCAD putting a height to it, but it's not really. It doesn't really have any height. It's a 2-dimensional object, so we can just rotate it, and it knows that the z facing up should be then dragged across the z-axis. So you don't have to rotate it to be in line, or to be I guess parallel or in line with the rotation. It knows that. Then if we add this translate, that puts it up there, and then we can uncomment all this, and then we get our pencil holder. And so this is like maybe a little bit too small, and we have the square size 4, the circle size 4. That's actually because the diagonal of the square. So because it's a square, we can just multiply this 4 times square root of 2. And there we go. There's a cool pencil holder. I think. If you wanted to go one step further, maybe you could take this and then add a mirror to it, and then mirror it about the Y plane. You could probably also do the X plane, and then that adds like a cool cross pattern to it. And that's real cool looking. Yeah. And just another thing that this kind of confused me for a little while is that like mirror, why would I have to duplicate this? Because I just want to like make a copy with the mirror. And that's just because mirror is like rotate or translate, or the other operations is that it's just mirroring it. We don't necessarily want to copy it. So there's a fancy, or a mildly fancy duplicate mirror function that I wrote that allows you to apply a mirror and also have it duplicate at the same time. But perhaps topics for another workshop. But I think with that concludes the OpenSCAD workshop. This is the first time we've ever ran this, so if it went well, let us know, please. If there's anything we can do in the future, or any future topics that you'd like to see covered, also let us know. And yeah, thank you.